In this video, we're going to do stoichiometry using the ideal gas law. So let's go ahead and start off with a bit of a warm-up. We saw the ideal gas law in a previous lesson, and so you should be able to answer this one by now. Remember, there's several formulas for gases, but the ideal gas law specifically is PV is equal to nRT, where R is a gas constant. And that goes into our second warm-up question, which is what is the ideal gas law constant and what are the units for it? So the ideal gas law constant is represented by the letter R, and it's going to be 8.314. And this is specifically if we're using Kelvin and pressure as kPa and also volume in liters. So our units are going to be kPa, liters, over mole Kelvin. And so those are the units, and when you plug that into your equation or your formula or your work you're doing, they'll all cancel out to give you what you're trying to get to in the end. So that is the ideal gas law constant, 8.314, with these units over here. So that's why when we do the ideal gas law, it's important to convert to your pressures to kPa so that this actually works out, your volumes to liters so this actually can be used, and your temperatures to Kelvin so this can actually be used. If you have different units of pressure, make sure you convert to kPa. There are other values of R you can use for different units of pressure, and there's a table for that, but for us, it's going to be easier just to convert all your pressures to kPa. So although we didn't really go into much depth with collecting gases over water, we briefly saw what it was. That's how you essentially can measure your volumes of gases produced during a lab by displacing water. And we saw that in order to figure out what your pressure of the gas was, you had to do your partial pressure of your gas is equal to your total pressure in the environment minus the partial pressure of the water vapor at that specific temperature. And that's the most important step before you can continue doing any more problems with collecting gas over water. But our focus in this lesson, after that warm-up, is to do stoichiometry using the ideal gas law that we saw earlier. And so stoichiometry is going to work much the same way it did in other units. We're going to write a balanced equation, convert all amounts into moles, and then use stoichiometry and mole ratios to find the unknown that we're looking for, and then convert that into something that we're looking for. For example, it might be the volume. It might be, it could be the pressure. But either way, we're going to use our PV is equal to nRT to do that, especially when we're dealing with gases. And so this little chart here, this graphic organizer is a way to allow you to remember what to do when you're trying to do stoichiometry. Regardless of what you start with, you always want to convert what you start with into moles. And so if you have mass, you can use this formula here. If you have concentration, you can use the N is equal to C times V. If you have pressure, temperature, volume, you can convert to moles using N is equal to PV over RT. And that's just a rearrangement of PV is equal to nRT. And then finally, once you have the moles there, you can use a mole ratio to find the moles of whatever you're looking for, whether it be a product or the reactant. And then you can convert to whatever desired value you need. So if you have the moles of what you found, you can convert to mass using this equation here. You can convert to concentration or volume using C is equal to N over V or an arrangement of that. So you can rearrange it to find the volume if you'd like. And you could also convert to pressure, temperature, volume of a gas if you have PV is equal to nRT. So this specifically is for a gas. That's what you want to use that for. And then the other ones you can apply in most situations, but typically when you're dealing with concentration or volume, you're dealing with a solution of some sort. So this here is just a flowchart to allow you to approach stoichiometry. We've done stoichiometry, these two sections already. Now we're just applying a third formula to stoichiometry, which is the PV is equal to nRT. So let's do a sample problem together where we want to go from volume to volume. Calculate the volume of CO2 that will be produced from 8.40 liters of oxygen at STP during the combustion of methanol over here. So first of all, I'm going to write out a balanced equation. We're going to put CH3OH plus O2. This is liquid over here, and this is gas over here. And let's just say this is a complete combustion. So that way I know my products are going to be CO2 plus H2O. And I can balance this. Pardon me. So I can balance this. I have one carbon, three O's, four H's. So I do need more H's here. So now I have four H's, but the problem is I have four O's. So that won't work out that way because here I need to have four O's as well. So what I could do is I could make this 3 over 2, and then I can multiply everything by 2 and get 2CH3 OH liquid plus 3O2 gas produces 2CO2 gas plus 4H2O. Now I think it's balanced. Let's double check. So two carbons. For hydrogens, I have, let's see, so eight hydrogens on both sides. For oxygens, I have 2 plus 6, 8. So 4, 8. So this is a balanced equation now. So that first step is just knowing how to balance your equations. And what we want to do is we want to find the volume of CO2. And now I know the volume of CO2. I'm going to have to find that using PV is equal to nRT. I know that because this is a gas here. It's not aqueous. It's not solid. So I'm going to use the PV is equal to nRT. And I can just rearrange that to get V is equal to nRT over P. Now, what other information do I have? Well, I was given the volume of oxygen. So that's going to be 8.40 liters. Something else that I was given for oxygen is the STP. So what that means is that I have a pressure of 101.325 kPa. I also have a temperature of 273.15 Kelvin. And it seems like the whole reaction's happening at that pressure and temperature. So that's going to apply to here as well. So my pressure is going to be 101.325 kPa. My temperature is going to be 273.15 Kelvin. We're going to assume that we're at the same conditions afterwards. And so what I want to do is I want to find my number of moles of O2 to help me find my number of moles of CO2. So to find the number of moles, I'm just going to put a little asterisk here. So I'm going to do that. So number one is we find everything. So write a balanced equation and write out all my steps here. Number two is going to be to find the number of moles of O2. And so that's going to be N of O2 is equal to, so remember we have PV is equal to nRT. So N is going to be equal to PV over RT. And so that's going to be pressure is 101.325 kPa times the volume, which is 8.4 liters, over the R, which is 8.314. And then we can put our complex unit there. So kPa liters over mole Kelvin times the temperature, which is 273.15 Kelvin. And so notice Kelvin and Kelvin cancel out, liter and liter cancel out, kPa and kPa cancel out, and we're left with moles in the end. So 101.325 times 8.40 divided by 8.314 divided by 273.15, and we get 0.374787133 moles of O2. And so now what we can do is we can use our mole ratios to find the moles of CO2. So we know that there are 3 O2s for every 2 CO2s. So what that's going to mean is that the N of CO2 is going to be our 0.375. I'm not rounding there really. I'm just writing that down as a rounded number, but in my calculator, I have the same number over here. Mole of O2 times 2 CO2 for every 3 O2s. I can cancel the 2's out. So I do times 2 divided by 3, and I get approximately 0.249858089 moles of CO2. Now, you don't have to write all those digits down. I just did that because I'm showing you what I have in my calculator still. I'm not rounding till the end. And now lastly, I can find my volume by taking my moles of CO2 and plugging it into this equation here. So volume is going to be my moles there, 0.24985 moles multiplied by my 8.314. I'm not going to put into units, but you can and do the crossing out, times my temperature, 273.15 Kelvin, over my pressure, 101.325 kPa. And so I get times 8.314 times 273.15 divided by 101.325, and I get 5.6 liters of CO2. So my step 5 is, therefore, the volume is approximately, I need 3 sig figs, 5.60 liters of CO2. So I wrote out an equation. I balanced it, so that's the first step. Then I wrote down all my information that I had about that equation for oxygen as a gas, and I converted that oxygen as a gas to moles because I want to use the moles of oxygen to find the moles of CO2. And then once I had the moles of CO2, I was able to apply it into the ideal gas law formula rearranged to find the volume of CO2. In the next video, we're going to take a look at a mass to volume problem. This problem here was a volume to volume problem. Regardless, we always convert to moles first, so then we can go ahead and do our mole ratios and then convert back to what we need at the end.